function composition actually shows up a lot more than you might realize. So for example, just in this function h of x, there's actually several layers of function composition going on here. There is a big square root function on the outside, right? That's one function. Inside of that, we have a cosine function plus x. And inside of that cosine, there's yet another function. So there's actually 3 layers of composition here, not just 2. And for every layer of function composition, we will use the chain rule. So you can see it's very easy to end up with a formula with multiple layers, and so we really do need to understand how you use the chain rule to kind of pick apart these layers and calculate the derivative of something like this. So let's find the derivative of this function h of x. So the derivative of the square root of cosine 5x minus 2 plus x. Okay, well, this definitely has an inside piece and an outside piece. So we're going to use the chain rule, right? And the outside piece is the square root function. So what is the derivative of that? Derivative of the square root function is 1 over 2 square root x. Okay, so now we can use the chain rule to deal with this very outside part. The chain rule says that the derivative of the square root with something inside of it is derivative of square root, so 1 over 2 times square root. And then into this derivative of the outside part, we put the inside part. So we have to put cosine 5x minus 2 in here, plus x. Okay, and then the chain rule says don't forget to multiply by the derivative of the inside. And the inside is cosine 5x minus 2 plus x. Okay, well, now we need to worry about this derivative, right? We still have a derivative left to compute. For this derivative, the operation that it sees isn't the cosine, it's actually this sum. Remember that the derivative sees the last operation that happens in an expression when you're sort of on the outside moving in. And the last operation here is the addition of this cosine piece with this x. So this first piece is going to stay the same, 1 over 2 square root cosine 5x minus 2 plus x. So we need to use the sum rule for the derivative, and the sum rule says it's the derivative of the first piece, cosine 5x minus 2, plus the derivative of the second piece, this x. But the derivative of x is 1. All right, now we aren't yet done differentiating because there's this derivative left to do. Now this derivative is seeing this cosine, and this cosine has an inside piece. So now we have to use the chain rule again. So 1 over 2 square root cosine 5x minus 2 plus x times, okay, now we're going to have a plus 1 all the way at the end. Now we're doing the chain rule, so derivative of cosine is sine. And then we need to put the inside piece into the derivative of the outside piece, so 5x minus 2. And then now we have to multiply by the derivative of the inside piece. So multiply by the derivative with respect to x of 5x minus 2. So you can see that we've had to use the chain rule again to handle this second layer of function composition. So 1 over 2 square root cosine 5x minus 2 plus x times sine of 5x minus 2, and then the derivative of 5x minus 2, you can use the difference rule and the constant multiple rule, it's 5 plus 1. So putting it all together, I guess we would write sine of, so probably move this 5 over here, 5 times sine 5x minus 2 plus 1 all over 2 times the square root cosine 5x minus 2 plus x. All right. So when we have more than one layer of function composition, right here we had an outside, an inside, and then an inside of the inside. When that happens, you're going to end up using the chain rule more than once. So here we use it once there and once here, in addition to some other derivative rules. Let's look at a couple more examples of that. So let's find the derivative of this, square root of 1 plus secant squared x. Now, it's a little tricky to see sort of how this is put together, why this has multiple layers of function composition, but it's because of this squared here. So remember that this is really an exponent for secant of x. So this is the square root of 1 plus secant x squared. Right? This makes it a little more clear why we have multiple layers of function composition. There's the square root on the outside, and then inside of that we have an expression with an exponent, and inside of the exponent is yet another function. So because we have sort of two layers of inside, we'll use when we go to calculate the derivative of this, we'll use the chain rule twice. All right, so since we're looking for the derivative of this function, let's find the derivative of square root 1 plus secant x squared. Remember, the square root function is really x to the 1/2, and so the derivative of that, you can use the power rule to find the derivative of x to the 1/2. It's 1/2 x to the minus 1/2, or 1 over 2 square root x. Okay, so to use the chain rule, we're going to differentiate the outside part. That's the square root, so 1 over 2 times square root, and then put the inside into this, so 1 plus secant squared x. Now we need to multiply by the derivative of the inside, which is 1 plus secant squared, let me write this as secant x all squared, like this. Okay, so 1 over 2 square root 1 plus secant squared x, right, times, now we have to just differentiate each piece here. The derivative of 1 is 0, and now we need to take the derivative of secant squared. But right, this is really a square function, and inside of that is secant, so let's take the derivative of the square function. The derivative of the square function is the 2 comes down, and you change the exponent here from a 2 to a 1, and then we put the inside piece inside of that, so that's secant x. And now we have to multiply by the derivative of secant x, but that is secant x times tangent x. Okay, so look, here we actually have a secant x times another secant x. So when we put all of this together, we have in the numerator, actually this 2 cancels this one. So in the numerator we have a secant times a secant, so that's secant squared x times tangent x over square root 1 plus secant squared x. All right, and this is as simple as we can get it. I don't think there's much else we can do with this one. It's tempting to try to break up this square root over the sum, but remember, square roots don't behave that way. Square roots just don't do that. So we're kind of stuck with this the way it is. All right, for another example of this function inside of a function, sort of 2 layers of nesting, let's look at this derivative. So derivative of 1 over sine of 2x plus cosine 2x. Now it might not immediately look like 2 layers of nesting, because after all, this is just a quotient. We could just use the quotient rule, but the quotient rule is messy, and I don't like using the quotient rule if I don't have to. And this time we can get away with not using the quotient rule. Instead, we can re-express this function that we're going to differentiate as sine of 2x plus cosine of 2x all to the minus first power. So I haven't done any derivatives yet. I've only rewritten this function using a negative exponent instead of a denominator. And you can see this lets me get away with not using the quotient rule. Instead, we're going to use the power rule. But we do, inside this exponent of minus 1 is a big old function. So we don't use the quotient rule, but we do have to use the chain rule. All right. So our sort of outside function is this function, the to the minus first power function. So use the power rule on that. The minus 1 comes down in front, and the exponent changes to minus 2. And then we have to put the inside in there. Sine 2x plus cosine 2x. And then we have to differentiate, multiply by the derivative of the inside, which is sine 2x plus cosine 2x. So minus sine 2x plus cosine 2x. This is a plus here. To the minus second power times. Now this is a big sum, so we have to differentiate each piece. So derivative of sine 2x plus the derivative of cosine 2x. All right. So minus, this first part doesn't change, minus sine 2x plus cosine 2x to the minus second power times, all right, now for this sine piece, it has an inside. Right, so we'll take the derivative of the outside, derivative of sine is cosine, put the inside into it, that's 2x, and then multiply by the derivative of the inside. And the derivative of 2x is 2. All right, plus, now again, for this cosine piece, it has an inside. So we have to multiply by, so we take the derivative of the outside, derivative of sine is, derivative of cosine is negative sine, so I guess this plus should actually be a minus. Put the inside into that, so 2x, and then multiply by the derivative of the inside, and that's 2 again. All right, so we could rewrite this sum to clean it up a little bit, but we're done taking derivatives at this point, right? All of the ddx's are gone, and what's left is just some algebra. So if we wanted to, we could maybe take this minus sign, distribute it over here, so that's going to give us 2 sine 2x minus, actually let's, sure, 2 sine 2x minus 2 cosine 2x all over sine 2x plus cosine 2x squared. All right, and finally we're done. So again, because we started out with 2 layers of nesting, right? Here's one big inside and then there are these smaller insides. Because we started out with these 2 layers of nesting, we ended up having to use the chain rule more than once.